So for a lot of you, this will be the last time I see you, just because grad students are busy. So we're going to do a goodbye letter. On hard copy. If you're online, you can on hard copy. About the class, you as instructor, Georgia Tech. Anything you want me to know. I'll be teaching this class again next year. This is the first time I've taught it in many, many years. To know. Yeah, what's up? Oh, thanks. Thanks, Jeremy. Okay, I'll have to repeat. So, yeah, we're going to take about 10 minutes for this, and then if you have, like I mentioned, if you have the laptops or your phone, we're going to do the CAOS evaluations. Georgia Tech keeps them for 5 years. Part of my salary depends on the evaluations. No pressure. No pressure. What? Oh, you could. It can be anonymous if you want. All the hateful letters you can keep anonymous. It can be anonymous, and the CIO's evaluations. You don't have to just write the numerical scores, especially the very last score that goes on my record for the next 5 years. And then we're going to do the class picture outside. I'm going to find a good place. We're going to do this for 10 minutes, and then we'll get started with the presentations. I read all these, so this is pretty important to me. So we'll just spend 10 minutes on this. Thanks. And if you're online, you can send. It'll be hard to make it anonymous, but I'd appreciate your feedback anyway. Does it want us to fold over the letters or use flat paper? You can do it very, like, at the end of the class, we'll just pass it down. Okay, I think. So you can continue these during the presentations. The class picture, there's a stairwell there. If you get the tall people to go to the back, if you're less tall, you go up to the front. We'll do 3 pictures. Laughing, serious, and your favorite mathematical symbol. Gesture with your hands. I used to do
Oh,
games.
you're not going to want that.
Not obsessed.
Mine's all about adding and subtracting.
But I used to do gang symbols, but someone actually showed a gang symbol, and then I had to answer that picture. All right, so we're gonna file out to the stairwell. It'll just take a minute, and we're gonna come back and start the presentations. I logged off whoever logged on here, so you'll need to log on again if you want to do it. Let's go out, and you can finish these during the presentations. You got this.
It's going to be outside?
No, it'll be indoor.
All right, good morning, and thanks for coming to today's presentation, and hope you will enjoy it and find some answers to the homework question too. And yeah, our topic is both dynamics and a whirlpool. My name is Alper. I will present with Raj and Shashank. Here's our contents, but briefly touching it, we'll just we'll discuss about our objectives, methodology to prove is the boat going inwards or outwards through the is it escaping from the vortex or not, based on different conditions, and we'll be giving you some analysis, both experimental and numerical. So our objective is, as I said, we'll be analyzing the trajectory of the boat, and we'll be showing you our prototype later on to show you under what conditions the boat goes inwards, or the boat is being captured by the vortex, or is it even possible to escape from the vortex? And we will be trying to develop some strategies actually to achieve stable and desired motion of the boat. We'll be doing this by adjusting the center of mass of the boat, simply. So I would like to introduce you to Charybdis, or Charybdis, however it's pronounced. It is a fictitious Greek mythological character, actually. It was believed that in the ancient Greek mythology, there is a sea monster called Charybdis. This creature is creating vortices, and the Odysseus particularly was trying to escape from the Charybdis and trying to go its destination without being escaped or without being attacked by the Charybdis. Actually, these are some pictures from the ancient Greek mythology. This is the Charybdis, how it looks like. Of course, it's lovely. And this is the vortex that's formed by the Charybdis. So we have found some very interesting links between the Greek mythology and the whirlpools. Actually, this whirlpool phenomenon is not something new. It looks like back in the Greek mythology, it was also known by the Greek sailors. And they were aware of the forces that was involved back then, which are gravitational forces, buoyancy forces, and centrifugal forces. They were actively using those, actually. And these are the 3 forces that are affecting our boat. Simply, we have gravitational force affecting at the center of mass, and we have the centrifugal force. This is also affecting to the center of mass, and we have the buoyancy force. It might affect anywhere in the boat, and these are the and these are the expressions of these forces. So keep these in your mind, because we'll be using these later on. So here is our experimental setup, basically. We have first, I would like to discuss about experimental procedure. We first turn on the stirrer and we create the vortex. We wait till the vortex steadies, because we want this. Then we start recording with the camera and we use the tripod. Then we release the boat, and we performed 5 to 10 seconds of recording to figure out is the boat either going inwards or the outwards. Then we stop recording. We did this many times actually to prove the phenomena. This is what our experimental procedure looks like. So we decided using ping pong ball actually for some reasons. The one reason is keeping the vortex center fixed, because if you don't use the ping pong ball, the vortex center shifts left, right, or upwards, downwards. This why it might be a good strategy to use ping pong ball at the very center actually. But we'll be showing you both cases. The second one is, of course, we didn't want to just dive into the water and pull the object again and again many times. So this is.
All right. So basically, we wanted to figure out a way to kind of see whether we actually are looking at an irrotational vortex. So, so to validate it, essentially, so we got a GIF over here, which is the most ideal way a irrotational vortex should look, and this is our experimental validation. So basically, you can see it's passing paths. I mean, crossing by each other. So basically, you're seeing an irrotational vortex. So that's how we validated it. So radially inward motion. So essentially, what we notice is that when you are having masses like properly balanced, so essentially you're seeing that the boat is going into the vortex. So this was the same case as well if you didn't have weights. You know, it will go into the vortex. So now let us look at a case where you probably have some differential weights. So, so radially outward motion. So this is when you would basically probably escape the vortex. So essentially what we did here is that we placed wheat dough balls basically in 3 locations. So this makes it more dominant basically for it to face towards the vortex. I mean, so the center of mass is basically inclined more towards the vortex. So this would give you an outward motion, essentially. So yeah. So again, this is again another video that shows you very clearly what is happening. If you notice, there's no weights in this video. So essentially, it is going into the vortex. So now you have like a mass, a weight at one location, and if you noticed, when that weight, when the center of mass is more inclined towards the vortex, it's going outwards. And once you see that basically when it is not towards the vortex, it is going inwards, right? Yeah.
So the question is, how is that possible? So for figuring it out, we need to actually create a torque balance, and we need to use the formations of the forces affecting that boat. If we do the torque balance with respect to point C, and we, after inserting the expressions of gravitational force, centrifugal force, and the body and the buoyancy force, we'll come up with this expression, which is m times the mass times the inward or the acceleration in the radial direction is proportional to this summation. This is just a constant, it's a positive term, but we have a term in here which includes the subtraction between the width of RC and RB. Here we have one assumption, which is the center of mass is below of the center of buoyancy. This is a very common practice of the ship industry. Actually, we have found out this information from literature. That's why we said ZC minus ZB is always negative. It's less than 0. So in order to keep this term positive, the only way of doing this is having RB greater than RC, which means fixing your center of mass at the towards inverse position. So this is the mathematical explanation actually to that phenomena.
So we have seen like our experimental results, and it's often very difficult to see the experiment itself and like make some results out of it. So what we did was we did image processing. So we extracted frames of the image, and then we tracked the center of mass position of the boat. So this is the case where we don't have any added mass. So it is going into the boat, into the vortex. So here you can clearly see that most of the data points are around the ping pong ball. And for the next case, this is the case where we have a center of mass here. Now the square here represents the trajectory of the center of mass, and the stars represent the trajectory of the boat. Now clearly here these are much more distributed and away from the ping pong ball, as you can clearly see. So then this term, we can assume this term to be constant when r is very much larger than the vortex radius. Now, but for certain cases, for instance, if we are close to, let me play this video. Yeah. So if we are very close to the vortex, it may happen that there exists a equilibrium position wherein the boat doesn't go in as well as it doesn't go out. So this is the concept of critical radius or equilibrium radius. And in this case, we have chosen a lighter boat because of less inertia. So if you have a boat with high mass, then this phenomena is unstable. So to make it stable, we essentially are using a lighter boat. Now, that was our experimental part. Now comes the numerical part of it. In experimental analysis, we did face several limitations. Like, it's often very difficult to always keep the center of mass towards the vortex. But in numerical model, we can go ahead with certain assumptions, and we can clearly see whether our understanding about the forces and their dynamics is correct or not. So we can discuss this model if we have time later. Only like 2-3 slides. Yeah. Okay. So this is our first model where our RB basically is greater than RC, which means that the radius of buoyancy force is larger than the radius of the radial position of the center of mass. Now in this case, we clearly see that the boat is going outwards. So this is the case where center of mass is towards the vortex. Now this is the second case where center of mass is away from the vortex. Now here you will clearly see that as time passes, the boat will gradually sink in. This is our vortex, so it will go towards the vortex. Now the important thing to note between these two observations is that we have started from the same radial position. So we have started from 3 meters. And even in this case we have started from 3 meters. And it is going less than 3 meters in the second case. So through this analysis we made sure that our understanding of forces and their dynamics are correct.
So finally, we'd like to conclude that there's a chance that the boat goes outwards if the center of mass is inwards. So if you guys don't believe us, like, you can actually go to the chapter's paper and you can actually read this statement they had. So basically, they came, they walked in the direction like towards the vortex by instincts. So that's what it is. It's a very old paper. So.
The inner side of the boat, and that's by just instinct without any calculation. That's why how they were escaping from the vortex. Yeah. If we have time, we can also show actually few experiments. Just 1 minute. Yeah. So what was the RPM? 360. Sure. Yep. Yep. It's exactly it's for the stability. It's not specific for cargo ships. It's just general for all kind of ships. Yep.
That condition actually arises from not the equilibrium condition. Like it may still be in equilibrium, but it is unstable equilibrium. So usually for this, people do energy analysis. So they find that it is actually an inverse speed. So whenever the center of buoyancy is below the center of
Stable.
yeah, it's unstable.
Oh, it's
when the
unstable.
center of buoyancy is beneath the center of mass.
Okay.
So usually center of mass is
Yeah.
everywhere.
Okay. Cool. Thanks. You lost the weight.
You have the screw loose.
You have the ping pong ball?
Yeah.
Sounds like so the center is actually rotational. That's the problem, right? The center's not.
Yeah. So yeah, the center is rotation.
Mm.
So there are actual real vortices in the ocean.
Yeah, I mean it generates like due to this differential pressure and oceanic currents and all. So there's some natural whirlpools and all in the ocean.
Yeah, it's catch-up dynamics. It's touching the ping pong ball.
I always thought Homer's Odyssey was like a analogy, some kind of analogy for like a.
Yeah, it has come up from the Greek literature actually.
Yeah,
So.
yeah. And Charybdis is supposed to be like his like lover or something like that, right?
In the paper that we have read, like
It's a monster.
it's
It
a
was
monster.
Like a monstrous creature.
Yeah.
A monstrous creature.
Like an analogy.
Well, sometimes it goes sour.
They have a scene like this in Pirates of the Caribbean too, I think.
Okay.
do.
They all run to the
Who's
center.
okay? All right. So Alper went first. Paul, are you more ready? Yes. Why don't you go set up too? It sounds like everybody's having some time. Paul, why don't you set up, and then after that will be whenever Aomidi. After that will be Aomidi, and then after that will be Lauren. Lauren actually wanted to go end in class because they're online.
Yeah, I have to.
So
We see
do late last.
That's right, because I'm
Lauren will be last.
Yeah. It's
So how'd you get that? The ping pong ball is pretty clever. It does. I do notice it does. These things do move, right? Why is that?
The ripples, the waves.
The center of the vortex. Why doesn't it kind of migrate?
Yeah, actually that is because if you had a shaft and
Yeah.
if the shaft is rotating with constant RPM, then this would not have happened.
It might be because of the stereotype.
Yeah, mostly the status
But it
geometry.
happens in your bathtub too. I guess your bathtub is not constant flow rate either.
There are a lot of uncertainties, that's why we just prefer keeping the ping pong ball at the center actually.
Oh, the shaft is actually moving.
Next time.
Like a mechanical engine.
We have 35 minutes left, and we have still 3 presentations at least. 1, 4. All right, Paul, I'm going to start your time.
Yes, but the screen. Is it on the micro? Oh,
Okay, so hello everyone. Today I'm going to present you my course project, which was about simulating the trajectory of a golf ball and studying various parameters such as the influence of dimples and the Magnus effect. So basically my summary will be structured around several points. First, I'll present the framework of my study and I'll introduce a bit the subject. Then I'll tell you how I developed a modeling tool on MATLAB and how I choose to go from a simplified model to a more complex one. Then I'll show you how I used current research on dimples fluid mechanics to get a more realistic model. And then I'll tell you about perspective for future research, and I'll conclude on my project. So golf ball dynamics is really interesting because it holds very promising grounds for computational sports science, which is a market that is really growing nowadays. And I found that this subject was interesting because it proposed an original, an educational approach to understand fluid dynamics and aerodynamics. So now for my study, I made several assumptions. First, I considered only a 2D trajectory on the plane. I also considered constant properties for the golf ball and for the media, so the air. And I also considered no wind. So in my study, I wanted to study in detail what was the influence of Magnus effect and what were the influence of dimples on the airflow around the ball. So I started with a very simplified model on MATLAB. So my first force balance was that the ball was only subject to its own weight. So it gave a classic parabolic motion, as you can see on the screen. So the ball is going really far. It's nearly 300 meters, so it's pretty unrealistic if you ever play golf. And for the initial conditions that I used for this model and for all the other ones were that the ball was originally placed at the origin of the axis. And for the initial velocity, I picked 55 meters per second with an angle of 35 degrees. It's basically what is listed in the standard rules of golf that we use for testing the balls and stuff like this. Then I introduced air resistance, so the drag force, as you can see on the screen. What was interesting about this drag force, it's that because of it, the flight equations became nonlinear because it involved the square of velocity. So I had to use a specific function on MATLAB, which is called ODE45, which is a very powerful function. And with this drag force, I found that, as you can see with the red curve, the distance covered by the ball is divided by 3. So it was a bit more realistic, but still pretty low for a golf shot. So then I chose to use Magnus force. So to remind you a bit how it works, I have a diagram and a video. And basically, the Magnus force is a phenomenon in a fluid dynamics that explains the deviation in the trajectory of a spinning object, such as a golf ball. So basically, when a golf ball is in a rotation and spinning, it's going to interact with the air surrounding it, and this interaction is going to lead to the creation of a pressure distribution gradient at the ball's opposite side. So the constant spin rate I chose of 180 radians per second led to the fact that the ball, as you can see with the yellow curve, was going higher because of the lift force generated by the Magnus effect. So yeah, with Magnus effects, the ball's rotation enables it to cover a greater distance. Now, what I wanted to study was the influence of dimples on the ball. So yeah, really quickly, I'm going to present you two videos. So the first video is about pro golfers trying to shoot with a smooth golf ball. And as you can see here, if I pass it quickly, the shots were not really good. So the first one, yeah, the trajectory is not really good. The ball does not go high and it does not go very far. And as a comparison with a golf ball with dimples, you can see that the ball can go as far as I think in this case it was 400 yards. So yeah, it's pretty big difference, and I wanted to understand what was the origin of the difference. So I used a study. First of all, I'm going to explain what are the basic difference between a dimpled ball and a smooth golf ball. So basically, the dimples on the golf ball, they are going to create small vortices at each of the dimples that is going to create a thin turbulent boundary layer of air that is going to cling to the ball surface, and this will allow the smoothly flowing air to the ball, thereby decreasing the size of the wake. So it's going to keep a little farther from the back of the ball, and thus it will reduce drag in comparison to the small ball, where the boundary layer does not cling to the back of the ball. So basically, it will reduce the drag coefficient by almost 2. To understand a bit more in detail how it works, because it's a very complex phenomenon, I used a study which is called the High Order Computational Fluid Dynamics Simulations of a Spinning Golf, and which was published by people from Stanford University. And it was really interesting because it was the first high-order CFD simulation of static and spinning golf balls at realistic flow conditions. And it used what we called implicit large eddy simulation, which is basically a mathematical model for turbulence used in CFD. Yes. Okay. Yeah, I'm pretty well advanced. So yeah, it was really interesting because it allowed for a really good mesh, which was able to capture a lot of different flow scales. And for this study, the simulation was advanced in time using an explicit 5-stage fourth-order Wunsch-Kutta time integration method, which is really high-order analysis. And so it provided new, more precise lift and drag coefficient values, which I was able to introduce in my model, and it resulted in the purple curve, that you can see here, which goes higher and farther than a smooth ball, which is pretty conclusive. So yes, so the perspective I had for future research, first for my model, I think it would be interesting to understand a bit more how Magnus effect works, to implement it in a more advanced way, maybe study the influence of wind, maybe study the influence of a non-steady spin rate, which would be more realistic, and maybe study a three-dimensional model, for example, to see the influence of the curve effects on the sides, such as you can see on a free kick in soccer. I would have loved also to do experimental validation calibration to have more realistic parameters. And I think that this research holds promising ground for biomechanics and player-specific interaction. So I think it could be interesting to study the interaction between a golfer's swing mechanics, launch conditions, and the ideal properties of a matching golf ball for maximum performance. So to conclude on this project, I created a MATLAB simulation with variable complexity. So that was interesting because I could compare the different parameters. I applied the Magnus effect to a concrete case, which was really interesting also because I was able to understand a bit more how it worked and what it affected concretely. And I also used recent research on dimples with high order CFD, so a pretty recent study with a lot of complexity. And I was able to introduce it in my model. So yeah, I think it was pretty interesting. So that's the references I used. And if you have any questions, feel free to ask.
Why don't they just use it in all the sports if it's so good?
Because it's really recent. They were implementing it to golf balls right now because it's a fairly easy model to apply it on because you can make several assumptions that make the model more easy. But I think they were talking about implementing it in hockey balls. I don't know how to say it.
Pucks.
Yeah, hockey pucks. Yeah, they were planning on doing the same with this.
You want to put dimples on hockey pucks?
No, but this type of study, it was planned. I know for the dimples because it holds very significant importance in golf. But for example, for soccer, the only goal of a soccer ball is not to go far and to go high. So there is not really points in doing this.
And how do they make it spin the right direction to get the lift?
The pro players, I don't know. I'm not.
Yeah.
Yeah, I think the golf clubs are designed to introduce the perfect spin rate, but yeah, I think it's a whole technique that I don't have, unfortunately.
Okay.
Yes.
One more question while the next person. Hey, Amelia, are you ready to set? Go set up. Ask questions.
You know, work for like cylindrical like objects as well.
Dimples on cylindrical objects. I think maybe it would, yes, because what's interesting about dimples is that it allows a thin turbulent boundary layer, and I don't think how it could not work with a cylinder problem. My problem was in 2 dimensions and it works, so I think it would be the same. Yeah. Okay, well, thank you very much.
You need a presentation. You need to present that view. That's right. We're just. Oh, you didn't open it yet?
Yeah.
Hey, this is Lauren. Can you guys hear me in the room?
Yeah, we can hear you just fine. You said you want to go at the end of class, right?
My meeting got moved now to 10:30, and our recording is 18 minutes long. So I'm not sure if you guys will be able to get to us today.
You can watch the first few minutes
Okay.
and then finish online. Which one was that? Like that?
It's not sure. It's supposed to show it differently here. I don't know why.
Just play it like this. Does someone supposed to speak in here?
Here, there
So, no, I'm
All right, let's just apply it this way. This looks fine. Go ahead. Ready?
All right, good morning, everybody. Yeah, so I'll be presenting on. My name is Ayomide, and I have two colleagues, Antu and Kono. They are not here presently today. So I'll be presenting on teapot effect. So teapot effect is something that we discussed even during the journal presentation, and well, it's a very important it's a very important effect that that has caused a lot of controversies among researchers, and some researchers propose some propositions for principles that guide this teapot effect, while some others are countering them. So we are trying to understand which one is which one is the correct one, which one is the correct proposition that is valid for this teapot effect. So the teapot effect started actually in 1956 by a scientist called Rayner. So what he did is that he argued that the teapot effect was not solely due to adhesion or surface tension. So, so he proposed two things. He said he observed two phenomena. And the first one is the liquid layer sticking to the solid wall, and also the anti-ballistic jet. So what he did is that if you observe at this side here, they submerged a curved a solid surface. They submerged it, they inverted it into fresh water, and they pour salt water solution on it. So with the aim of seeing maybe the salt water be able to go down the stream, but it observed that the salt water were clinging to the curved surface of the material. Same thing in the base here as well. So continuation. So he now proposed that the sticking phenomenon was due to the vortices. That is not due to adhesion and is not due to surface tension. So that when the fluid is pressed against the wall of the kettle or the spout of the kettle, it is due to the rotational kinetic energy of the vortices that are being formed around, as seen in these pictures, as seen in this place. So he rejected that the air pressure explanation that has been given to maybe why this is effective is not the reason. I need to rush because of time. So Keller, another researcher, a year after 1956, when Rayner published his, he came up with another proposition where he said that is actually due to air pressure differences. So which is like opposite to what Rayner said. So, and this is similar to the Quanda effect. If you know Quanda effect, it is that situation where the water or the fluid that is coming out of the spout of a kettle is following a curved path instead of following a very straight path. So this is example of Quanda effect as seen here, where we see that the fluid is trying to stick to the flat surface here, and this is just the hypothetical situation where we believe that there is no detachment in the fluid. So we have some audio. Let me play the audio here. Okay. It's not playing. It's not playing.
Down. The flow from a spout is shown in Figure 4. To construct the flow of Figure 4, we first determine the complex variable and complex potential as shown on the slide. The flow from a spout is shown in Figure 4. When the pressure PC has... The flow from a spout is shown in Figure 4. To construct the flow of Figure 4, we first determine the complex... Keller's qualitative explanation of the teapot effect is as follows. Keller's qualitative explanation of the teapot effect is as follows.
He says that the flow velocity is greatest at the lip or at the tip of the spout of the kettle. So, and he says that by Bernoulli principles, the pressure is lowest. Surrounding air then pushes the liquid against the lip by its atmospheric pressure. those are the propositions by Keller in 1957. And these are just like the mathematical concept that guides the the something. So we have the complex variables, as we all know, and the complex potential equation. So then at the origin here, which at this point D, which is the edge of the lower plate, and also this is the upper part of it, which is at the H. So this is just the equation. I don't want to spend too much time on this equation. So when the PC has the minimum value of pressure, all right, thank you.
So the Zoom people could hear it. We just can't hear it. That was only up.
I'm sorry. Surprising.
Hey, Lauren, you're right. I don't think we're going to be able to get to yours today because of this issue.
Yeah, unfortunately, I don't know. It was working fine. For some reason, it's not working today. Not much else I can do. I'm sorry.
It's okay. Thank you very much.
You're going to carry the show. Carry the whole business.
It's okay. It's okay. So.
Lauren, we're probably not going to. Can you send your talk to the WhatsApp, to the group me, and we'll probably just we'll look at it together.
Yeah, I will do that after the class. I'll do that after the class.
Yeah, I was talking to Lauren.
Should I?
Lauren's online.
Oh, okay.
I point to the ceiling and you're like.
Talking to God. On the real thing.
Can't hear. You're just gonna have to tell us. Hey, Lauren, you're right. There's some technical difficulties, so send your your presentation to the group me, and we'll look at it after class.
Okay, sounds good.
All right. So when the PC has the minimum value of pressure, what happens is that the flow.
You either talk or you maybe turn off the volume for this because we can't hear you over there.
All right.
You can go ahead. Just talk.
So when the PC has the minimum value of pressure, what happens is that the flow does not touch the upper part of the plate, and it behaves as shown in this picture here. So the upside down flows, what happened here is that the flow velocity is constant far from the edge, this edge here, under the lower plate. And the pressure variations due to gravity, it becomes very important. So, and in this situation, the flow is only possible if the height is less than the pressure divided by the rho g. Otherwise, what will happen is that the pressure becomes negative. And with that, what happens is that cavitation will occur. So this is just like a sketch of, I don't want to waste too much time on this, please. It's very disturbing. I'm sorry. So, and these are just the equations that guide the concept. All right. Let me just move to the demonstration. I'm sorry. So, all right. So there are some things that Keller's propose that for teapot effect, what happens during teapot effect is that we have low flow rates that is stable, but to make it desirable, what we have to do is to have to convert it to transition to high flow rate. So to do that, there are some conditions that we can do to do that by increasing the curvature of the lip here. You see the curvature is increased here. So with this kind of design, the tip-pot effect will be reduced. And also by increasing the contact angle. So, and how can we increase the contact angle? By maybe applying hydrophobic material like butter, applying it here. If you observe it, the contact angle it displays has increased, varying from this one. All right, so, and another one is also by increasing the slope angle, as I said. So these are just the demos. These are very important. So we have three different kind of kettles that we use for this experiment. So we use the thinnest material, which is a ceramic, and this is the picture. And another one here with a very long spout and smaller openings. And the other one is the one with the shortest spout. So, and this first one here, what we observe is that it has this high curvature. It's very curved, and it has this highest slope angle. And remember, I mentioned that by increasing the slope angle, it helps us to be able to reduce the tip-pot effect. So this is the medium one for curvature and for slope angle, and this is for the one with the lowest curvature. So what we did here is that if we tilted the kettle at an angle of 45 degrees to be able to have a positive slope angle, and when we do that, we observe this straight pouring of liquid. So this is the effect when we applied. This is when we applied the hydrophobic material, the butter, when we applied it to the layer of the surface. What you observe here is that there is no dripping, there is no tip-pot effect here at the tip because of the hydrophobic material that we applied. So this is for the second type of kettle, the kettle with a longer spout, right, but not made from ceramic material. So we applied butter like we did for the first one, but we still notice a bit of tip-pot effect. Although not as strong, but not as good as the first one. So the material that we use is also affecting the tip-pot effect situation. So this is for the third one with a very short spout. We applied it and we see. All right, cool. So, and another experiment that we did is that we performed the underwater tip-pot effect. That is, we placed the kettle under the water and put a dye solution into it, and we also observe tip-pot effect as well, as could be seen in this. It's just so sad that this thing doesn't play. So, anyways, our key takeaways is that in as much as we have different controversies from different researchers, some of them say vortices is what is responsible for this tip-pot effect. Others claim to be that is the air pressure, while there are others claim to be adhesion or cohesion. So I'm not a professor yet, so I can't argue with any of them. But from our research, some things are, we get some things from our own research. Number one, if we pour the tea at a faster rate, the tip-pot effect is reduced. That's number one. Number two, if the kettle, the spout of the kettle has higher curvature, you reduce the tip-pot effect as well. Number two. Number three, if we use thinner material like ceramic for the kettle, it also reduces the tip-pot effect. Then number four, by applying hydrophobic material like butter to it, it reduces tip-pot effect as well. Thank you very much.
Questions for AMD while next set up. There's vortices. Can you actually see those with your dye? Do you see the vortices?
Yes, we did. It's just, I don't know, maybe when I send the video, it's just not. It's so sad.
I thought you have flow passing from the plate. You won't have vortices.
No, we experience vortices in our presentation. I'd love to show you.
Do I start now?
Yeah, and we'll it is 10:36. We go 1 minute over, you'll have 10 minutes.
Hi, I'm Layla, and Brian from Distance Learning will be joining in via audio recording. We'll be talking on the stability of beer foam. So a little bit of background. Beer foam or head and its stability are essential to the quality of a beer, and it adds to the visual appeal and enhances the mouthfeel. And how the beer is poured often determines how much foam you get. And the amount is often dependent on the drinker's preference. So the photo on the right shows the same beer being poured 3 different ways, and the one on the right is just all foam because it's apparently Czech people like to drink beer that's all foam. Regardless of the amount of head the consumer prefers, the longevity or the stability of the head is usually always desired. And so basically we wanted to first understand the physical concepts behind the formation and stability of the foam, and then see if we could do some beer pour experiment to determine if the pour angle not only affects how much foam it creates, but also how long the foam persists. And that's just go back. Okay, so part 1. Okay, so a foam is basically a dispersion of gas bubbles in a liquid, and bubbles burst when they reach the surface. So when the bubble production rate is much faster than the rate that they burst, they start to accumulate on the surface, and that creates the foam. And a stable foam is usually dense with tightly knit small bubbles. And so bubbles do not nucleate spontaneously. A nucleation site is usually present. It could be imperfection on the glass surface, such as a dust particle or a scratch. And the photo on the right shows a special glass with a single nucleation site etched on the bottom of the glass, which produced this one train of bubble going up. And fun fact, it was estimated by some researchers that there are between 200,000 and 2 billion bubbles released in a half pint of lager before it goes flat. And this just shows the steps in bubble formation. So first, gas pocket forms in this, in the nucleation site. So imagine this. Oh, my bad. How do I do a pointer? Oh my God. There you go. Okay. So imagine the solid is the surface of the glass, and then this is the nucleation site, this crevice. And then a gas pocket is going to form from a dissolved CO2 from beer, and then a bubble is going to grow out of it, and eventually it's going to detach from the surface. So the size of the bubbles generated is a function of the nucleation site radius and surface tension, density, and acceleration due to gravity. And the nucleation site size is the biggest contributing factor in the size of the bubbles. So in order to create the most stable foam, you want to have the smallest bubbles, so you should minimize the nucleation site size. Then after bubbles form, they'll rise to the surface because they're less dense than the beer that's in. And in beer terminology is also creaming or beating. It also adds to visual appeal, and it replenishes the foam. And the frequency of bubble release and rise is quantified by this initial nucleation activity function, and it's dependent on the carbon dioxide content, the surface tension, and the density. And so this photo is it's of a detergent solution, and it was taken 30 minutes after it was shaken, but it's actually very similar to beer foam, and it shows the structure of foam. So the foam on the top is called dry foam because more liquid has drained from it, and the films intersect at these plateau borders that intersect at these vertices. And dry foam is made out of bigger polyhedral bubbles, whereas wet foam, as seen on the bottom, have smaller, rounder bubbles because the liquid inflated the plateau borders and the vertices. And this is just a photo showing the collapse of foam, and with the arrow pointing in the in increasing time. So first, bubbles will look rounder, and then after some time, it starts to deform because the liquid is around it is going to start to drain. And then after a lot of time, it's going to start looking like this polyhedral shape, like on the top. And then the two main mechanisms that cause this are drainage and disproportionation. So as soon as a foam is formed, liquid starts to drain from it due to gravity. And any factor that slows the rate of drainage will increase foam stability. And it can be slowed by increasing viscosity or decreasing bubble size, but it cannot be stopped because of gravity. And the rate of drainage is a function of the density, the gravity, length of plateau border, as seen earlier, and the thickness of the film, and the viscosity. And then the next one is disproportionation, which is also known as coarsening or Oswald ripening. It's not the same as bubble coalescence and is usually much more significant in beer foam. Basically, bubbles collapse due to gas diffusing from smaller to larger bubbles, as described by the Young-Laplace law, which states that the gas in the smaller, more highly curved, smaller bubbles are of a higher pressure. And so this photo on the right shows what's going on. In a foam, you'll have bubbles with different sizes, and then the gas in the smaller bubbles will diffuse into a bigger one, and then the smaller ones will collapse, and the bigger ones will grow bigger, and then eventually it'll start to look like this. And this is a video just showing what's going on. And so as you can see, the smaller ones sort of get swallowed by the bigger ones, and the bigger ones just keep growing. And then after oh my God, I'm sorry. I was trying to skip in time, but in the interest of time, I'll just skip it. Yeah, so, and then this proportionation is also quantified by the de Vries equation, which calculates the change of radius in a bubble, and it's as a function of time. And it's dependent on the gas constant, the temperature, the diffusivity of the gas, and the solubility, the pressure, and the film thickness in between the bubbles. So disproportionation can also be solved by decreasing the gas solubility or diffusivity. For instance, nitrogen is much less soluble than carbon dioxide, so by introducing a little bit of nitrogen, as little as 15 to 20 parts per million, will improve foam stability, but it might alter the texture of the foam. Okay. And disproportionation also accelerates drainage. So now we're on to the...
This is the 3D model for the testing apparatus. This was designed to control and measure the pour angle of the beer bottle while keeping the glass constant. Then we would measure the beer head produced at different time intervals from the pour to determine an optimal pour angle. In the initial trials, the goal was to use the testing apparatus to measure pour angle and beer head. After several attempts, several issues became obvious. The beer glass was too small.
Yeah, so basically we tried to build this apparatus that holds the beer glass stable while, holds the beer glass at certain angles while we keep the glass stable, but it was causing a lot of issues with the pour.
In the initial trials, the goal was to use the
pour, so
testing
then instead of changing the angle of the beer glass, we started changing the angle of the glass. And then we poured it with the glass at different angles. So this is putting the glass at an angle of 30 degrees. And then
the video shows the standard. These images are from the standard 10 and 20 degree pour.
Similar
As
results,
you can,
but it seemed like with a decrease in keeping the glass more straight, produced more foam. And then this is just putting the glass upright, which is what we call the 0 degree pour. And the standard meaning not purposely making the flow rate faster or slower. So then now this is angling the glass at 20 degrees, but then trying to produce a faster flow rate, which also created a lot of foam, but then it disappeared much more quickly, as you can see in the photo on the right here. And then this is angling the glass, keeping it up straight and then pouring it at a slower flow rate, which created a lot of foam as expected, but it also persisted for much longer than pouring it at the same angle, but with just a regular flow rate. And the foam also clung to the glass a lot more, which is also very interesting. Yes. So this is a table of all the the foam heights that we got. And so the last 4 pours all lasted for at least 4 minutes. The slow 0 degree one lasted for 8 minutes, which is a lot longer than the rest of them. A likely best pour technique is a mix where you go half a regular flow rate down the glass, and then you do a fast one down straight in the beer down the middle. Let's just have a conclusion. But yeah, so basically the slow 0 degree pour produced the longest lasting head. And with better optical equipment, I think we could have made some more conclusive conclusions on if it's because of the smaller, more tightly packed bubbles that reduce the drainage rate. And factors such as the cleanliness of the glass could have also impacted the bubble nucleation. So thank you.
No. People can linger around and ask questions if they have time. Oh, I said leave the presentation.
Oh.
People can
I'm sorry.
ask questions if they have time.
Okay.
If you gotta go, go to the next class. Basically, what we learned from today is you cannot assume the audio is going to work. So whoever's going to present is probably going to have to be prepared to present the whole thing. We'll continue these on Monday. We have 1, 2, 3, 4, 5, 6. But we won't be spending time on evaluations and stuff, so we should have no problem getting it done. That'll be, again, a 10-minute, maybe 10 to 12 minutes with questions. If you got your letters, you can leave them in a pile here on your way out. If you didn't do the COS evaluations, please do it. I usually have around 80% response rate by pestering you. I have a question. You said that sometimes the head persists for longer.
Yeah, so when we did the pour, yeah, so when we did the 0 degree pour and then we tried it out with a normal flow rate and a slow flow rate, the slower flow rate, even though it produced initially about the same amount of foam, the slower flow rate produces foam that lasted significantly longer than just a regular flow rate. So it was hard to see from just eye inspection. That's something that we didn't anticipate, that it's a lot harder to make conclusions about foam without better optical equipment. Yeah, so in the conclusion side, so I suspect that it has something to do with the fact that it produces much smaller and more dense bubbles that impeded the drainage much more. Yeah, I think that's a likely reason.
The osmolar ripening is happening, and that just takes up time.
Yeah.
Smaller bubbles. Yeah, I can imagine that's more drag.
Yeah, because if you look at it's kind of hard to tell, but it looks like the foam, you can see that the bubbles are really, it's very solid looking than other ones, whereas some of the other pores produce bubbles that are just kind of big and more sparse. And this looks a lot more solid. So I think that's a likely reason of why it lasted a lot longer.
And there's more, you have a higher Reynolds number with higher pouring rates.
Yes.
And you have more turbulence.
I think that released more carbon dioxide and released more foam from the get-go, but it didn't necessarily persist longer.
To make these bubbles, it has nothing to do with those little cavitation points you have on the glass. Like if you have no glass, you're still going to make foam. It's water hitting, it's liquid hitting liquid.
Yeah.
Okay. All right, thanks everybody.